Oh, I forgot to press the button. Come on. Oh, well, fine. Let's try it again. Law. Oh, my Lord. Oh. I don't have a lovely voice. Let's try this. Hmm. Hmm. All right, fine. Welcome to a short discussion on waves, the basics of waves. I'll do another one for some detailed stuff in waves. So I'm going to change a couple of things like, yeah, good, like that. Now this wave has some certain characteristics that we should talk about. If we say that's about the equilibrium level of the wave, well, this wave has what we call an amplitude, measured from the middle, from equilibrium, not the whole height, all right? From equilibrium to this thing called a peak. This thing's called a trough. Okay? Now this, from here to here, how do you know what that is? There's two things that might be, but notice, this is measured in a number of seconds. This is what we call a period, or seconds per cycle. Now, from that period, we could calculate something that we call the frequency. F is 1 over t. And so that means it's going to be cycles per second. All right? Now, since we know this is a sound wave, we know the speed that it went at, and so therefore we can relate its frequency and its wavelength. So notice again, this from here to here is not a wavelength because this is an amount of time. All right? But again, if I could calculate, measure that wavelength, which I could, watch down at the bottom. Right? See where it says delta t? I'm sort of finding the time from peak to peak, and it's about that. Right? That's the period. We could use that to find the frequency, and we could say, well, the speed of sound in here is about 345 meters per second, and therefore we could find the wavelength of that wave. Okay? Make sure you can use that equation. Make sure you can do this, and make sure you can recognize make sure you can identify an amplitude, all right, or a period, or stuff like that. Okay, now there's a different kind of graph. Here we are talking about wave basics. Well, it might not even be a graph, but here's a wave on a string, and the string's an actual object that takes up actual space. And so if we measured how far it was from trough to trough, or from peak to peak, that would be what we call wavelength, literally a distance. Okay? But when we graph something about a wave as a function of time, that peak to peak is an amount of time, and that's called a period. Okay? So that's the super duper wave basics. Some of the other stuff we talked about is, here are these two waves. Let me clone this bad doggy. These two waves right now, because they are lining up peaks with peaks and lining up troughs with troughs, we say these are in phase. Okay? If I were to do this, and take this one and shift it over half a wavelength, we'd say that this is half a wavelength out of phase, or 180 degrees out of phase, or pi radians out of phase. phase. I think the only one they really ask for is that one. Okay, and even if we look at two places on the same wave, we could say that, well, that and that are in phase. They're really 360 degrees out of phase by my view of it, but that's okay. We would say that this place and this place are out of phase, or they have a phase difference of 180 degrees. They typically don't ask you much different than either 360, like that's a full wave, or 180, that's a half a wave. Okay, that's some stuff about phase. Now, other things that we should talk about with waves. One is interference. All right, and so you got a wave coming like this. Whoops, you got a wave coming like this. And when they interfere, they make a bigger pulse for a moment. Here's pulse A, here's pulse B. You know, there's a snapshot in time here in the middle. And then, you know, pulse B keeps going, pulse A keeps going. We call this constructive interference. Right? This has the amplitude A plus B. Right? Destructive is, you know, the opposite of that. Looks like this. You got an A coming, you got a B coming. Oh, we'll call them X and Y. Right? They come together, and well, this one might be a little bit like that. Because notice that Y is a little taller than X is. So there's this little when they interfere right there, and that would kind of be like Y minus X. And then, you know, Y keeps going and X keeps going. So this would be called, we would call destructive interference. Okay. What else? What else? You can also see that in some different ways. Like if we said that here's a wave coming out of a speaker. These things are called wave fronts. This is kind of like literally like a peak and 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 a peak. Each one of these lines represents a peak. All right. If you had a separate wave that say was coming this way like that, there are places like right here. There are tons of them. But right there, peak and peak interfere. That would be constructive interference. A little bit harder to tell, but like say right here. Notice that's a peak right between two peaks. So that would be a peak and a trough interfering, and that would be destructive interference. Okay? You know, if two sounds are interfering constructively, the sound gets louder. If they're interfering destructively, the sound gets quieter. If it's two light sources interfering constructively, the light gets brighter. If they interfere destructively, the light gets dimmer. All right? So waves can, good evidence for light acting like a wave is that light sources can interfere. All right? Any waves can interfere. Any waves can also do what's called diffract. All right? And so wave comes along like yay and hits an obstacle. Well, wave, you might think it only continues straight along, but what it does is it'll kind of like do that and like bend around there. And, yeah, so light, or waves, excuse me, can bend around obstacles. Or light can also, did I say light again? Waves, any wave can also get to what we call an aperture and expand through that aperture. Notice it doesn't change the wavelength. Wavelength stays the same, but it just, that's how cameras work. Um, Light hits a little hole and then spreads out and hits either a piece of film back here or more typically now a computer light sensor. Okay? So that's just called diffraction. You just should know that that's what diffraction is. I think I'll sort of stop there for this one, and I'll come back with another one about light specifically and how it can reflect or refract. The one other thing I will talk about before that, though, is what's called the Doppler effect or Doppler shift. All right. If the source of a wave is moving this way, the waves that it emits will still go the same speed in all directions. But you could end up, the source of the wave can end up catching up to the waves in front of it and kind of running away from the waves behind it. All right, so out here, if you're a dude standing here, I mean, the waves haven't gotten to you yet, but when they get to you, you will, so I'll say detector, observer, better, observer detects higher frequency / pitch. The dude out here, this observer detects lower frequency / pitch. So this is when the sun, you're standing here, just standing there eating an ice cream cone or something. That's an ice cream cone. And the cop car comes roaring by you. Right? Am I taking too long to do this? Probably. Right? So this dude screams by you. Right? Yeah, sort of. It goes right when he passes you. You hear high pitch, lower pitch. Okay? So sure, it gets louder, but we're not talking about that. The change in volume is not what we're talking about. We're talking about that when this thing comes towards you, it's the waves that it emits, it's catching up to those waves. You hear a higher pitch now. Now it's running away from those waves. You hear a lower pitch. Okay? Fine. That's the Doppler shift. Thank you. Thank you.